All right, let's dive right in. Today we're talking about one of the most brilliant and frankly necessary ideas in the history of science, Niels Bohr's model of the atom. And this wasn't just some small correction. No, this was a radical, reality-bending proposal that solved a problem so big, it basically threatened the existence of, well, everything. And that problem really starts with a simple, kind of terrifying question. I mean, think about it. If the basic laws of physics that we see all around us also apply to the super tiny world of atoms, then why is anything solid? Why are we here? Why hasn't all matter just folded in on itself and disappeared in a puff of smoke? You see, to really appreciate Bohr's genius, you have to understand the sheer panic that was setting in around the early 20th century. Physicists were staring at their own rulebook, and it was telling them something impossible. It was telling them that the universe as they knew it simply shouldn't exist. It all kicked off with this really beautiful, elegant picture from Ernest Rutherford. So after his famous gold foil experiment, he suggested that an atom is basically a miniature solar system. You've got this tiny, dense, positive nucleus playing the part of the sun, and then you have these little negative electrons orbiting it like planets. It's simple, it's intuitive, it just feels right, you know? But, and this is a huge but, this beautiful little model had a fatal flaw, a catastrophic one. According to the laws of physics that everyone knew and trusted, any charged particle that's accelerating, and orbiting is a form of acceleration, has to give off energy. So that little electron should be bleeding energy, losing speed, and spiraling into the nucleus in like less than a trillionth of a second. Poof! Game over. If that were true, every atom in your body would collapse right now. So physics is broken. The universe shouldn't exist. And into this absolute mess steps a young Danish physicist named Niels Bohr. And in 1913, he did something incredibly bold. He didn't try to tweak the old rules. He basically said, what if, on the atomic scale, the universe is playing a completely different game with a completely different set of rules? And here are his 3 new rules for the universe. First, he just declared that electrons have special safe zones, these stationary orbits where, for some magical reason, they don't radiate energy. They're just stable. Rule 2, you can't just orbit anywhere you want. Only very specific distances from the nucleus are allowed. And Rule 3, electrons can jump between these allowed orbits, but it's not a smooth ride. They instantly leap, and to do so, they have to either absorb or spit out a particle of light, a photon, with the exact right amount of energy for that jump. This core idea is called quantization, and it is the heart of all modern physics. Here's the best way to think about it. In our big, everyday world, things are like a ramp. You can be at any height you want along that ramp. But in the quantum world, it's a staircase. An electron can be on step 1 or step 2, but it can never, ever exist in between the steps. Everything comes in these discrete, chunky packets called quanta. Now you might be thinking, this sounds totally made up. It's so arbitrary. And you're not wrong, it was a wild guess. So how on earth could Bohr prove something so strange? Well, it turns out the proof was hiding in plain sight the whole time. It was coded into the light from the simplest atom there is, hydrogen. See, for years, scientists knew this weird thing about hydrogen gas. If you zap it with electricity, it glows. But it doesn't give off a smooth, continuous rainbow. Instead, you see these very specific, super sharp lines of color. It's like an atomic barcode. And for the longest time, nobody had a clue why. This is where Bohr's model just clicks into place beautifully. That quantum leap he talked about, when an electron jumps down from a higher step, a higher orbit, to a lower one, it has to shed some energy. And it does that by spitting out a single photon of light. And since the energy of those steps is fixed, the energy of that photon is also fixed. And a photon with a very specific energy has, you guessed it, a very specific color. And here is the absolute genius of it. This wasn't just a nice story. Bohr did the math. He calculated the energy for a jump from the 3rd orbit down to the 2nd. His math said it should produce a photon of red light with a specific wavelength. And when they looked, boom! There it was. The jump from the 4th orbit to the 2nd, it predicted a blue-green line. Perfect match. His model was like a mathematical machine that printed out the exact barcode for hydrogen. It was a stunning, unbelievable success. So, was that it? Was Bohr's model the final answer to everything? Well, No, not quite. But its importance is just impossible to overstate. It was the essential bridge that finally got physics out of the old, classical world and into the bizarre new reality of the quantum realm. Let's be fair. On the one hand, it was an absolute triumph. It solved atomic collapse, it perfectly explained hydrogen's spectrum, and it gave us the key idea of quantization. But it definitely had its limits. It didn't really work for any atom bigger than hydrogen, and it couldn't explain why only certain orbits were special, or the even weirder fact that electrons sometimes act like waves, which was a discovery just around the corner. Still, even with those flaws, what he accomplished was so fundamental, so world-changing, that for saving the atom and giving physics its very first real foothold in the quantum world, Niels Bohr was awarded the Nobel Prize in Physics in 1922. His model wasn't the final picture, but it was the one that made the rest of the picture possible. Which brings us right back to that idea of a bridge. Bohr's model was that crucial first step, the thing that got us across the chasm from the physics we can see and touch to the strange, counterintuitive rules of the quantum world. So if his idea was the bridge, what kind of weird and wonderful landscape is waiting on the other side? Well, that is the world of modern quantum mechanics, and trust me, it's a story for